So let's get into the last two sections of chapter 16, where we're going to talk about Gauss's law and how Gauss's law relates to the electric field. So a little motivation for studying Gauss's law. Well, remember in the previous examples where we had a dipole, we had two charges, right? And we found the electric field at, some distance, away from those charges, right? We found the net electric field, and it turns out it was to the right. All right, so that was, although I showed you some shortcuts, it can be a pretty complicated process to do that for a whole bunch of charges, right? For example, if we wanted to find the electric field somewhere outside this group of proteins, there's so many charges here, right? I mean, thousands, millions, maybe even. So calculating the electric field in that way, one vector at a time, would be extremely time consuming. And Gauss's law, once we learn it, Gauss's law is a method you can use to find the electric field if you happen to know the charges that exist in this object, which we do, which we would, because we know what atoms these proteins are made of, and we know how many electrons are on them, right? So it's actually quite a quick calculation to figure out how much charge lives inside of this protein. And so Gauss's law provides a way to calculate the electric field if you know how many charges are in a surface. Okay, a surface, like if I were to surround this by a sphere, the surface of the sphere. And so this is just giving you kind of a brief idea of what we're doing here. So, and that's basically what this second slide says, right? We use this approach called Gauss's law. It's an alternative way to express Coulomb's law, but what it helps you do is it helps you find the electric field by a new quantity called the electric flux. So let's talk about what flux is and what the electric flux is before we get into Gauss's law. Okay, so we're going to kind of back up a little bit. We're going to talk about electric flux and how to calculate it. So in general, flux is a mathematical term. It's a mathematical operation. It actually has a couple of different definitions, but in this case, the definition of flux is taking a vector, okay, and seeing how much of that vector passes through a surface area, A. And the way we do this calculation is we take the vector of interest and we see how much or what part of that vector has a component that is in the direction perpendicular to the surface area. Okay, so that sounds kind of like complicated. Like, okay, what are you talking about? Here's an example. So if we look at water passing through a pipe, okay, this velocity vector V describes the direction that the water is moving. And you can see that in this situation here in this picture, all of the water possible is passing through that area. And so the total flux in this case would be the amount of the area, so it would be like length times width, times the full amount of that velocity vector. Why? Because the velocity vector is parallel to the perpendicular part of the area, okay? So there's like a lot of steps here, parallel to the perpendicular part, okay? In other words, the component of the velocity perpendicular to the plane is the full V, and so therefore the flux is A times V. So now what if our area is flat and we're passing the water over top this rectangle? How much of the water is going to go through that area zero water, right? Because it's passing over it. And therefore, no component of the velocity vector is perpendicular to the plane of the frame. So zero amount of that vector passes through that area. And so what you can see here is that to describe this area, we are describing this area with its perpendicular. So what you can do is you can actually characterize an area with a vector, okay? This vector, A, would be equal to, its magnitude would be equal to the area of that shape, in this case, a square or rectangle. And then the direction would be whatever direction is perpendicular to that. So if this was an X, Y, and then Z was coming out of the page, and this would be like in the Y direction. Okay, so the way we characterize an area in terms of finding the flux is we characterize it with a vector that is perpendicular to the plane. Okay, so that's why you can see that the V vector is perfectly perpendicular to the area, of the plane, the area vector, and therefore no flux. There's no flux. Why? Because there's no vector penetrating that surface area. And so now, well, what if the vector is at an angle with respect to the perpendicular to the plane? Well, then the amount of vector that passes through that area is going to be given by AV cosine theta. And so how can we see that? This V cosine theta, this is the component of V that is parallel, spelled that wrong, parallel to a perpendicular. Okay, and I'll use this little T symbol to signify perpendicular. So remember how we were breaking down vectors into components in those previous examples? Well, I can break down this V component into a component that is perpendicular to A and parallel to A, right? And then if this is my angle theta, then you can see with trigonometry that the length of this side, if this is the total vector V, like this is the magnitude of the vector right here, the hypotenuse, then this is V cosine theta, right? Because it's the adjacent to that angle. And that's where the V cosine theta comes from. Okay, so now in terms of flux, electric flux, the situation we are talking about is not velocity of water, and it's not, random vector V. The vector that we care about is the electric field vector. And how much of it passes through some surface area, A. And here's the perpendicular. Okay, and so now we are talking about how much electric field vector passes through a surface area, and we're going to call that the electric flux, and we're going to use the symbol capital Phi to denote the electric flux. Okay, and so here's the formula or the expression for that. It's the area of the surface times the component of the electric field that is perpendicular to the surface. So we're going to multiply the area times the component of E that is along this direction, okay? So I want to just get rid of the red, right? Remember, this would be the component that we care about for E perpendicular. This purple one I'm about to draw, right? This is the component of E that is parallel to the area. We don't care about that one. We care about the component of E that's perpendicular. And as I showed you in the previous slide, right, if we call this angle theta right here, and we get this triangle, make this triangle here like that. right? I'm copying down the electric field vector triangle. This was the magnitude. This was E parallel, which you don't care about. This was E perpendicular. And you can see it's on the adjacent side to the angle, and therefore it's expressed as hypotenuse times cosine theta. Why? Because remember, adjacent over hypotenuse is the definition of cosine theta. And so all I did was you move the hypotenuse up here to solve for adjacent side. Okay, so a little bit of vectors coming back at you. This quantity flux, we've really analyzed it mathematically, right? We totally understand where it comes from in relation to the electric field vector and the area. So what does it mean? Well, it means how much electric field is passing through an area. Okay, that's what it means. So here we can see the three cases. We already examined these three cases in terms of the vector V and area, right? In terms of the water analogy. Well, here they are in terms of the electric field analogy. And you're going to see, right, in case number one, when the area vector, which remember is the perpendicular to the area, when it is in the same direction as E, theta is 0, right? Cosine of 0 is 1. And we're left with the flux. Yeah, there we go. Theta is 0. Phi is AE, theta is 0. Right? And the total flux is AE. And so now what if the electric field just glides over the surface of the area? Well, there's no component of the electric field that is in the perpendicular direction, right? So in other words, this is 90 degrees, theta is 90, and then the flux is going to be 0 because there's no component of the electric field passing through the area. And then finally, if you have your electric field at some arbitrary angle theta with respect to the normal of the surface, then you're going to have the expression AE cosine theta, which we got from looking at the components of E, looking at instead of breaking the components into X and Y, we're breaking the components into the component along the perpendicular and the component parallel. Okay, that would be E parallel. This would be E perpendicular. And since E perpendicular is on the adjacent side of that right triangle, then E perpendicular will equal the magnitude of that vector E, which is the value of this hypotenuse. Let me just move this out of the way. Right, the magnitude of that, the magnitude of E is the hypotenuse of that right triangle, so we get this, which is just me solving it from this. Okay. So when we calculate electric flux, specifically, for Gauss's law, the area that we are using is not like a real area. It's not like a real object. We are choosing an area that's going to be convenient to us. Okay, it's just help us visualize the area in question. So now let's talk about an electric flux through a closed surface. So instead of it being a flat rectangle, we're going to use a surface that is completely closed, and in this case, a sphere, right? A spherical shell is a completely closed-in surface. So it encloses a volume. So that's how you have a closed surface if the surface completely encloses a 3D volume, okay? So let's find the electric flux through a special case. The case of a point charge, okay? We know that point charges produce electric fields, right? In the previous section, we just looked at what the electric field looks like outside of a point charge. And so if we draw our imaginary surface, which is this sphere right here, here's our imaginary surface. And we want to find the flux through that surface. Well, we should probably draw our E field vectors to get an idea of what it looks like. And remember, they're all vectors pointing directly away from the charge. And E field vectors, they exist in every point in space, but we obviously don't have all day to draw a million billion vectors, so we're just going to draw a few convenient ones to get an idea. And so those electric field vectors, you can see in relation to a sphere, those electric field vectors are perfectly perpendicular to each little tiny region. If we were to break up this sphere into little tiny square regions, you can see that the E field vector is perfectly perpendicular to those little surface regions. And so what does that tell us, right? That tells us if we were to add up, do the flux, we would get EA here, we would get EA here, we would get EA here, where the E's would all be constant. Why is that? Because remember, the magnitude of the electric field is KQ over distance between charge and place. We want to know the E field squared. Well, what is that distance? It's all equal to R, the radius of that sphere, right? So everywhere you have an E, the value of that E is KQ over R squared. It's constant. And then all these A's, well, if we add them all up, all these A's are going to add up to the surface area of a sphere. So the total flux that we would get from this calculation, it would be E of a point charge times the area of a sphere, surface area that is, right? There's the total flux. And it would be positive. It would be a positive value. Why? Because the electric field vector is pointing out of the surface. So positive flux, a flux that is greater than 0 means that the vector, in this case the E vector, is pointing out of the surface. And the value of that flux is going to be the electric field of that point charge at that distance r times the area of the sphere. So now let's look, what about a negative point charge? Well, it's the exact same thing, except the direction of the electric field is different, right? It's 180 degrees different than for a positive charge. So with the electric field pointing inward, we now have a negative flux, okay? The magnitude of it is going to be the exact same thing, but the sign will be negative for a negative point charge. So what if you have a positive charge and a negative charge in the surface? Well, everywhere you have an E field pointing out, you're going to have an equal and opposite direction of the E field pointing in. And they're all going to cancel each other. Trying to find, oh, here's this cancellation, right? Those two cancel, these two cancel, these two cancel, and your net flux is going to be 0. What if you have two charges, plus and minus, outside of the surface? Well, you're also going to have 0 because you're going to have the cancellations again. Okay, the cancellations are going to be a little bit more difficult to picture, but you're going to have the cancellations again. And then the physical, that's the mathematical reason, but there's a physical reason why, and that's because there is no charge enclosed in the surface. Okay. So that is how we calculate the electric flux through a closed surface, where the electric field that we're using to calculate the flux is the electric field created by a point charge. Okay, so if you read through these slides, everything I just explained is basically what I just spoke to you about in just on that first part of the slide. right? The areas, we add up all the areas. The electric field is constant. Okay, we add them all up. And so what do we get? We didn't finish doing that. So, right, in that previous slide, I told you that the flux was all the electric field times all the area of the sphere added up. The electric field we know is KQ over R squared. The area of the sphere, remember I said was R, and so the area of a sphere is 4 pi R squared. And so now when you, get rid of some, do some algebraic, simplification, your final result for the flux is 4 pi KQ, okay, which is basically this right here. Okay, and what is that number? It's a constant number, right? Let's look at that value. What is 4 pi KQ? Well, it's a bunch of freaking letters, right? But what do they mean? Well, this is a number. K is the constant, right, that we've been using, 8.99 times 10 to the 9 Newton meters squared, Coulomb squared. And Q is as a number as well. It's just the value of the charge, right? So the flux is constant. The flux is constant. It's a number. It's just a value. It's just a number, right? It doesn't change with R. It changes with Q, but that's just changing, the value of the charge inside, and that just makes your number bigger or smaller. But there's no dependence. What I'm trying to illustrate to you is that there's no dependence of phi on anything, okay, other than just the charge that's inside. So that's a really powerful statement, okay? That's what I also want to, it's a very powerful statement. The flux, okay, so like if you have a positive charge here, if you decide to make your surface a sphere of radius r, if you decide to make your surface a cube, okay, you decide to put that guy in the cube, if you decide to put that guy off center in the cube, not directly in the middle, okay, doesn't matter. Your flux is going to come out to be 4 pi KQ, okay? So, let me erase this stuff. This next got the concept is going to illustrate what I just told you. It's going to make a lot of sense. Okay, so let's say we have a certain charged particle placed in the center of a sphere. And we've calculated the net electric flux, and it's phi naught. Okay? If now, instead, we double the radius of the sphere, should have made that sphere a little smaller. So now we're going to double the radius of the sphere. What will be our new flux? I'll call that flux 2 because we doubled it. What is the flux 2? What is the flux now? Okay, how does the flux change if we make the surface bigger? Well, let's churn through it. So we saw that the flux is equal to the electric field times the area of the surface. Okay, the electric field due to a point charge, KQ over the distance between the charge and that surface, which was just the radius of the sphere, right? R squared, times the area of the sphere, which we know to be 4 pi R squared. So now, so what is that? KQ, 4 pi KQ. So what about over here? So now our radius is 2R. So the flux over here is going to be the electric field at this point, okay, right? Some distance 2R away. So I can write that maybe as E at 2R, where this was E at R, times the area of the surface, okay? So what is the electric field at a distance 2r away from a point charge? It's kq over 2r squared. What is the surface area of a sphere of radius 2r? It is 4 pi 2r squared. Guess what? Boom, those guys cancel again. And we have mathematically proven that the size of the surface doesn't matter. The flux is constant, right? The flux is identical between those two surfaces. And that's the power of Gauss's law. That's where the power is coming from. And in the next section, we'll see how to use it, okay? But now you can see the power of it because the flux is independent of the type of surface you choose. Okay, so if that was a little confusing, all of these got the concept questions are explained at the end of each chapter. There's like a paragraph for each one. So definitely when it's study time, you go to those and read those, okay? So, let me see. This slide might be a little bit redundant. What happens if we replace with the dipole? We talked about this. This is I realize that this is a bit redundant here. As far as the way I decided to speak about it in the first slide. So if all of these slides here are just reiterating what I spoke about, and you can just read them, if you do better at reading or if you do better at listening to me, or both, you want to do both, read through these slides, but it's pretty much, I explained it all already. Okay. So, to make Gauss's law useful, we really need our shape to be symmetric with respect to the charges inside of them, right? In order for the flux to come out to be very nicely as E times A, the charge producing the electric field lines, we need the symmetry of all that, right? If this is the electric field lines are radial. They have radial symmetry. Spheres have radial symmetry, okay? So we need that to match up so that when we add up all the little fluxes, that it comes out to be that this value is constant with respect to the surface. Okay, so in order for it to work out, we're gonna be doing basically only spheres. There is another example of a cylinder, but for the sake of time, I can't cover every symmetrical type of surface. So we're going to focus on spherical symmetry, which goes with point charges and electric fields that come out of point charges. So focus on this case only, okay? And so here's the Gauss's law statement, okay? So what we saw right in the previous slide is this. We calculated the electric flux, and we saw that it was equal to 4 pi kq, okay? So that this is exactly what this equation says as well, except all we did was we replaced k with 1 over 4 pi epsilon naught, because we've been using k, and that's exactly what k represents. K is shorthand for all of this, 1 over 4 pi epsilon naught, okay? And so when we substitute k for 1 over 4 pi epsilon naught, you get a really nice and clean and pretty version of Gauss's law, okay? And which states that the electric flux through a closed surface is equal to the charge enclosed divided by a constant called the permittivity of free space, epsilon naught, okay? Here's its value. I don't think these units are right. So look up the units, they're in the book. I can't, I get it backwards. I think it's coulombs on the top, coulomb squared over Newton meter squared. That could be correct. Something like that. Okay, so K is just related to epsilon naught in that way. All right, so this is just basically the exact same thing as this, what we talked about in the previous slides. But because we have been using K for so long, we wrote it as K. But the way that Gauss's law is normally written, it's written with epsilon naught. Okay, just to make it more powerful looking. So, right, so that is Gauss's law. Gauss's law tells us that the flux through the electric flux through a closed surface is simply equal to how much charge is inside that surface divided by epsilon naught. So now let's look at those cases where we had a positive charge, we had a negative charge, and then we had a positive and a negative charge enclosed in the surface. Okay. Now, instead of adding up the E field vectors, right, we're like, oh, okay, the E fields are pointing out. Oh, they're all pointing in. Oh, some are pointing out, some are pointing in. Instead of doing that calculation now, we can jump straight to the right-hand side of Gauss's law. What's the flux over here? Oh, it's just whatever the charge value of Q is over epsilon naught. What's the flux over here? Oh, well, Q is negative, so the flux is going to be negative. Q over epsilon naught. What's the flux over here? I don't need to add and see all the cancellations of the electric field vectors. The flux over here is going to be positive Q plus a negative Q, which gives me a big fat 0. So now you can calculate the flux without having to worry about the vectors, and all you need to worry about is adding up all the charges inside. Okay? So in this figure, this is just a figure representing Gauss's law, right? So the net charge enclosed in your surface, which we call a Gaussian surface. Remember, the surface is imaginary. The surface is there to help us do a calculation. So the net charge enclosed in a spherical Gaussian surface is Q. Therefore, the flux through the surface is Q over epsilon naught, right? Don't need to calculate the flux here, flux here, flux here, flux here, add it all together. Don't need to worry about the vectors. All we need to worry about is what charge is inside of that surface, okay? And so now, well, what if we, use a weirdly shaped Gaussian surface like this bubble here? Okay, well, guess what? The flux is still going to be Q over epsilon naught. Because we are, instead of adding up all these fluxes, we can simply use the right-hand side of Gauss's law. Okay, so that's what this text here is basically saying. So the shape of the surface doesn't matter. Let's look at this, got the concept. When a certain charged particle is placed at the center of a sphere, the net electric flux through that surface is phi naught. So we said, okay, this is like what we did before, right? We got this guy. Now, what if instead of a sphere, we use a spheroid, American football shaped object, okay? What would be the flux through that surface? Well, what we just saw in the previous slide is that it doesn't matter the shape or size of the surface, right? The right-hand side is Q over epsilon naught. So it's going to remain flux, whatever Q over epsilon naught is, right? So the shape doesn't matter. There's our units. Okay, Coulomb squared over Newton meter squared. I knew it would come up here somewhere. So, right, so permittivity of free space, that's 8.85 times 10 to the minus 12. It's just another constant, right? And what we've been using it, but just as in form of K. All right, so we've already been using it. So, let's look at this, got the concept. So we start off with our charged particle in the center of a sphere. If a second identical particle is placed outside the sphere, what would be the new flux through the surface? So we place a particle out here. what would be the new flux through the surface? Well, Gauss's law tells us that the flux is equal to Q enclosed over epsilon naught. He's not enclosed, right? So our flux is still going to be the original value of Q over epsilon naught. Okay, so placing charges outside the surface does not change the flux through the surface. Okay, so to wrap up this section, we talked about electric flux, what it is mathematically, and we related it to, instead of water, velocity of water, we're like, no, we're going to do electric flux, which is how much electric field vector penetrates an area, right? And the way we characterize the area is through the perpendicular direction of the area, right? So the part of the area that we care about, you know, and we normally, when we care about an area, we care about its area, okay, right? Its area, how big is the square? But when we are using flux, what we really care about is the direction that the perpendicular of the area makes, okay? We also care about the area value, but we care about it in the perpendicular direction. And so when we calculate the flux, we need to find the component of E that is in the same direction as that perpendicular. All right? And what we physically saw is when we did that mathematical operation, what the end result ended up being, because of the nature of the electric field being 1 over r squared proportionality, and the area of a sphere being r squared proportionality, what we saw is those r squares canceled, right? The r squares go away, and then your flux is independent of the shape. And your flux is simply Q over epsilon naught, right? Or 4 pi kq. So that's the powerful statement that Gauss's law makes, is it says that the electric field penetrating through any area around a couple of charges is simply equal to the charge enclosed divided by a constant. And in the next section, we will talk about how to use this, okay? How to use this. In certain situations, of course, right? In certain situations, Gauss's law helps us calculate the electric field and helps us determine how charge is distributed inside of that surface that we draw. So we can look at a spherical charge distribution, okay? So up until now, we have been dealing with point charges, right? And the assumption that's made about a point charge is that it's like really, really small and it takes up 1 point in space, okay? Well, what if now, instead of a point charge, we have a 3-dimensional sphere, not to be confused with the Gaussian surface, okay? This is like a metal ball, okay, that I've electrified, okay? We have a sphere, a 3-dimensional sphere that is charged. And let's say that charge Q is distributed uniformly over the volume of that sphere. How could we figure out the electric field around here? Like, what kind of information can we get from this uniformly charged sphere? Well, what's nice about using a sphere is that it's symmetric. So something that's spherically symmetric means you can rotate it at any angle around its center and it will be exactly the same. So that's good, because remember, to use Gauss's law, we need symmetry. So the electric field that is caused by this 3-dimensional ball is also spherically symmetric. So if we break up this ball into little pieces that each have a little bit of charge, well, the electric field, since this happens to be a positively charged ball, is going to point directly away from those little pieces. And so what you can see is that the electric field looks a lot, it's pretty much almost identical to that of a point charge, okay? They all point out and away from the surface. And the electric field, in this case, only has a direction that is along the radial direction. So when we say the electric field points, radially away from something, that means that this electric field vector only has a radial component, which we denote with ER, okay? There's no other, there's no component going this way, which we would call the theta component, right? All components of the E field is pointing in the radial direction. So this is all just kind of a preamble, right? A setup. We're describing now the electric field of a three-dimensional object, and then we're going to see how Gauss's law helps us with that, okay? So now in this figure, let's say that I want to use Gauss's law to tell me something about the sphere, okay? How would I do that? Well, I would draw my Gaussian surface in a shape that is symmetric with the object. In this case, it would be a sphere. And then I would go about calculating the flux, okay? And what I would see is the flux, without knowing what E is, I can see that everywhere, what I know is the direction of E, and that everywhere around that surface, the direction of E is perfectly perpendicular to the surface. So I know that the total flux through this red surface is going to be whatever E is times the area of the sphere. Okay, so if I don't know E, that's okay. I know it's the same value everywhere because I know that it's the same distance from either the center of the sphere or the surface of the sphere, right? Because it's a radially symmetric object. I know that E is a constant. And I can do the same thing. You know what I can also do is I can also place a sphere inside the sphere, right? I could place my Gaussian surface inside the sphere and do the same calculation, okay? And I can see that the electric field is in the same direction, perfectly perpendicular to every point in space of my surface. So I know the flux is going to be E times A of my sphere there, okay? And so now the question is, that's the left-hand side of Gauss's law, right? Using the electric field in the area to calculate the flux. Well, what does the right-hand side of Gauss's law tell us? Well, the right-hand side of Gauss's law tells us that the flux is equal to the charge enclosed over epsilon naught. So what I can do is, right, I independently figured this out on the left-hand side of Gauss's law. Now I'm going to use the right-hand side of Gauss's law, and then I'm going to put them together, okay? So let's figure out, so what is Q enclosed in this situation, part A? Well, Q enclosed is, the entire sphere is enclosed. The entire sphere has charge, big Q, right? So, big Q over epsilon naught. Now I can set my left-hand side of Gauss's law to my right-hand side of Gauss's law equal to each other. So I see my electric field that I don't know is equal to the area of the sphere that I chose, which happens to be little r. It's equal to the right-hand side, which is the charge enclosed, big Q over epsilon naught. Now I can solve for E. And if I use K, boom, the electric field outside of a physical three-dimensional charged ball, okay, not a point charge, but a charged ball, is actually identical to that of a point charge, right? This is the same as a point charge. So, right, I never told you what the electric field outside of a three-dimensional spherical ball is, but I used Gauss's law to show you that, guess what? It's exactly the same as a point charge. Now, what about inside of this three-dimensional charged ball? Let's do the same thing. All right, let's set the left-hand side of Gauss's law equal to the right-hand side of Gauss's law. So I have my E field that I don't know, and then I have the sphere, and then I have the area of the sphere, which is little r. And then what do I have on the right-hand side? The right-hand side is going to take a little bit of work because I don't know exactly how much charge, right? If the entire ball has charge Q, well, my surface is not enclosing the entire charge. My surface is enclosing a portion of that entire charge. So I'm going to need to do a little bit of math to figure out how much charge is enclosed, okay? And it's really easy because this is a uniformly charged ball. It's uniformly charged, meaning the density of charge is equal. So I can just use a ratio to figure out how much charge is in there. And so in order to figure out the ratio, I need to think about what's the volume of a sphere, of this whole sphere. Well, the volume of this sphere is, you may remember, 4/3 pi r cubed, right? That's the total volume of the sphere because we're using big R to denote the radius of the whole sphere. How much volume is enclosed in my Gaussian surface? Well, that is 4/3 pi little r cubed, right? That's how much is in my surface. And so the amount of charge in this part, well, it's going to be a ratio of this to this, right? Only a fraction of the total sphere is enclosed in the surface. So only a fraction of the total charge is enclosed in the surface. And that fraction will be, so now when I set my right-hand side equal to my left-hand side, this Q enclosed, that's going to be equal to the total charge times the fraction that's enclosed. The fraction being 4/3 pi little r cubed over 4/3 pi big R cubed. That's going to be my Q enclosed. And so now I can plug everything in. Big Q, so we got some stuff canceling here, right? This stuff, that goes away. And then I'm left with little r cubed over big R cubed. And then there's my epsilon naught. Don't forget him. I'm going to do some more simplification, right? Because I need to move this term over, the 4 pi r squared. E equals, so I have Q r cubed over epsilon naught 4 pi r squared big R cubed. I'm going to get some more cancellations. Okay? And what I find is that the electric field inside of that three-dimensional, charged ball is 1 over 4 pi epsilon naught big Q little r over big R cubed. This guy right here. Okay, so this graph is a summary of these two equations, right? We figured out the electric field outside the sphere. So the electric field when the sphere, Gaussian sphere, is bigger than the physical sphere, right? There it is right there. That's what we found out over here. And then, but when we're inside the sphere, the electric field is going to be a ratio of the volumes of the charge, right? Because only part of that charge is enclosed in our Gaussian surface, and we end up with this value. So that's how Gauss's law helps us find unknown electric fields. Okay? We use the left-hand side of Gauss's law. We leave E as a constant that we don't know, but we want to find. And then we basically fill out the blanks of all the rest, right? What's the area of our Gaussian surface? How much charge is enclosed? Solve for E. And that's what we did right here. So that's what these slides are all, I just did it all for you in that one slide, but these go through all the steps that we just did together. So read through that. Okay. Unless you understood what I did, but you see here's our ratio of the volumes, right? We did all that. And there's our final result. We just did it all in one slide. I talked you through it. And so here is the other symmetric shape that you can use to solve for E. But I don't want you, we're not going to do disk. Something has to give, right? This is a very long chapter, so don't worry about I think basically the rest of this section. Don't worry about it, okay? We're not going to be covering the electric field of a disk. Okay, I know that starred there, but we are going to be skipping this. And we're going to be skipping excess charge on conductors. Unfortunately, we just don't have all the time. So the part of chapter 16.7 that I want you to focus on is how Gauss's law can be used to calculate the electric field in certain cases. The case being spherical charges, right? Three-dimensional spherical charges. Okay? So that completes chapter 16. And, when it's time to study, definitely look at all of the concepts, okay, they're in the book, they're in the slides. Look at all the examples and how I framed the examples to be a test question, okay? And then you will be in a good spot for the exam, for the portion of the exam on chapter 16. Okay, and of course, email me if you have any questions about the material. Come by office hours, okay?